Hey guys, welcome back to Chili and in this video we're going to see how we can perform various operations like addition, multiplication, adjoint or inverse on matrices. Okay, so the question arises is why do we need to study matrices for machine learning? Okay, so the thing is that many machine learning algorithms like simple linear regression can be easily solved by using matrices. And if you have less number of data points, then using matrices to find values like its slope and intercept is very productive since it gives us faster results. And there are many Python libraries like SciPy and NumPy that can calculate such operations on matrices very easily. But it is very important for us to know how these operations work as we are going to use matrices and its concept a lot in machine learning algorithms. So this is just a video to brush up concepts on machine learning, and this is my blog if you want to check it out, and I post articles regularly on it, and I'll put the link in the description. Okay, so let's get started. The first part is the definition of matrix. An m by n matrix is a rectangular array of numbers with m rows and n columns. Here you can see that first example is of a 2 cross 2 matrix, so it has 2 rows and 2 columns. You can see it here. And the second example is of a 2 cross 3 matrix that has 2 rows and 3 columns. Okay, you can see it here easily. And the third example is of a 3 cross 2 matrix that must have 3 rows and 2 columns. Okay, so this is right. Okay, so the fourth one is matrices with only one column are called column vectors. So here you can see that it is only one column, so it is called a column vector, and it doesn't matter how many rows it has. Okay, so moving forward to point 5. Matrices with only one row are called row vectors. So here you can see that it has only one row and it doesn't matter how many columns it has. Since it is one row, it is going to be called a row vector. Okay, so the notation to write m cross n matrix is given here, and you can see here that the rows goes from a11, a21 to am1, so it must have m number of rows, and the column goes from a1, a12 to a1n, so it must have n number of rows. Okay, and a11 is the element at first number of row and first number of column, and a1 is the element at the first number of row and nth number of column, and amn is the element at m number of row and n number of column. Okay, so moving forward to second part, that is addition and multiplication of matrix. So first we are going to see the addition of matrices. So the thing to keep in mind here is matrices can be added only if they have the same dimensions. So we cannot add matrices like one matrix is of a 2 cross 3 size and the other matrix is of 3 cross 2 size. So the matrices must have same dimensions to be added together. So we can add matrices like 2 cross 3 and 2 cross 3, or we can add matrices like 3 cross 3 and 3 cross 3. Means it must have the same dimensions. And you can see the matrix addition is pretty simple. We just have to grab the element at each index and we just have to add it simply. So it's easy to understand. So moving forward to the next point, that is scalar multiplication. Okay, it multiplies every number in matrix with a scalar value. Now a scalar value can be any number from our data line, or what to say it, a number line. So a k is any number from our number line. So it just multiplies each value with a scalar value. Okay, moving forward to point 3, that is matrix multiplication. So matrices other than scalar can be multiplied only if the number of columns of the left matrix is equal to the number of rows in the right matrix. Okay, and the multiplication of matrix is not commutative. It means that the multiplication of A and B does not equal to the multiplication of B and A. That's a point to keep in mind. Okay, so here we are going to see how we can multiply the matrix actually. Okay, so we go like this. We take the first row and the first column, for this point, and for this point we go like first row and second column, and for this point we go like second row first column, and for this point we go like second row and second column. Okay, and you can see that suppose let's say that this matrix is a matrix, and this matrix is a B matrix, then multiplication of A and B is not equals to the multiplication of B and A. You can easily see it here. Okay, so we can say that the matrix is not, multiplication of matrix is not commutative. Okay, so now let's see how we are going to find these values here. Okay, suppose we want to find the value of Cij, where I and j are, let's say, number of sorry, the row and column value. Okay, so and k equals to 1, and it goes from 1 to n, and we are going to add it together. So here is the addition sign. Okay, so suppose we want to find the value of C11, that is the element here. This one is the C11 element, first row and first column. So here it how it works. So it goes like A11 into B11. So this is A11 and this is B11. So multiply them, that gives us AE. And next we have to go for the second iteration, since this is a 2 cross 2 matrix. So n is going to be 2. So now we have to add for k equals to 2. So it becomes A12 into B21. So this is the value of A12, that is B, and this is the value of A21, since it is in row 2 and column 1. So we have to multiply it. Okay, so this goes like same for the rest of this. Okay, so moving forward to the third part, that is the special matrices. Okay, so the first point is a zero matrix. So all elements of a matrix are zero, then it's called a zero matrix. That's I think pretty easy to understand. Next one is the identity matrix. The elements on the diagonal must be 1, and all the other elements rest other than the diagonal must be equals to 0. Then it's called an identity matrix. Okay, so moving forward, multiplying any matrix with identity matrix does not change the result. Okay, so if we multiply matrix A with I, or if we multiply identity matrix with A, then it does not change the result of the original matrix, that is going to be the same, A. Okay, so the next one is a diagonal matrix. A diagonal matrix has only non-zero elements on its diagonal. So it's a kind of like an identity matrix, but in identity matrix the diagonal values must be equals to 1, but here it can be any value, and the non-diagonal elements must be equals to 0. Okay, so the next one is a band matrix. Then how it is defined is all the diagonal elements must be non-zero. So here is how we find the diagonals of a matrix. So this is the main diagonal D1, D2, D3, and this is the second diagonal called A1, A2, and the third diagonal is B1 and B2. Okay, so this is an interesting matrix, that is a band matrix, and all the diagonal elements must be non-zero. So main diagonal, the secondary diagonals must be non-zero. Okay, then moving forward to upper triangular matrix. So it must form a triangle. You can see here ABC and this ADF forms an upper triangular in a matrix. So if the elements like if this are 0, then this is going to be upper triangular matrix. You can easily see a triangle here that is formed on the upper side of a matrix. Same like this, there is also a lower triangular matrix. So in this it is pretty easy to understand that it must have the lower triangle non-zero and the rest of the elements as 0. Okay, so I think this is very easy to understand. Okay, so moving forward to part 4, that is transpose matrix. Okay, so how do we find a transpose of a matrix? So the transpose of a matrix is a pretty simple operation. Okay, so to find the transpose of a matrix, we just switch the rows and columns of a matrix, or of a matrix we want to find the transpose of. Okay, so let's understand by an example. See, here this is the row 1, A11, A12 up to A1n. Then in the transpose of the matrix, our row shifts to or switches to column. Then in our transpose matrix, it will be our column 1. This is the row 1. Then in our transpose matrix, this is our column 1. And this is our row 2. Then in our transpose matrix, it is going to be our column 2. And this is our last row. Then it is going to be our last column. So transpose is a very pretty easy to understand operation. Okay, so in other words, we can say that the element Aij, then if we transpose the matrix, then the element Aij is going to be Aji. Okay, so what is this? Then we can see here that if we take A12 here, then this is A12, and if you transpose it, then it is going to be at A21, then it is going to be at A21, that is here. Okay, so I think this is easy to understand. Now here is an example of a transpose matrix. So the rows are basically converted to columns. So here is the row, so here is the column 1, then CD is the row second, then this CD is the second column, and EF is the third row, then EF is the third column. Okay, so moving forward, now this is a interesting function or operation on matrix, the transpose of a transposed matrix. If we take the transpose of the matrix and again take the transpose of the matrix, then it is going to return us our original matrix. Okay, let's take it by an example. So here our matrix is 1 2 3 4. So our transpose matrix must be, the column will be 1 2 and the second column will be 3 4. And if we take the transpose of it again, then the first row will be converted to first column, that is 1 3, and second row will be converted to second column, that is 2 4. So you can see that the value of transposed matrix transpose is going to be equal to the value of original matrix. Okay, so I think it is easy to understand. So moving forward to the third point, that is transpose of matrix addition. Okay, sometimes we have operations like this, like we have addition of a matrix and then we have to transpose it. Then it is very easy to understand that we just transpose both of the matrix and add this, and it will be the same result. Okay, so let's check it. See, A equals to 1 2 3 4 and B equals to 5 6 7 8. Then A transpose is pretty easy to find. So, and B transpose is also pretty easy to find. Then A plus B equals to 1 plus 5 means 6, 2 plus 6 means 8, 3 plus 7 means 10, 4 plus 8 means 12. Okay, so this is fine. Now A plus B transpose equals to 6 8 in the column and 10 12 in the second column. Okay, now adding the value of A transpose plus B transpose gives us 5 plus 1 6, 7 plus 3 10, 6 plus 2 8, and 8 plus 4 12. So here you can see that the value of both of these are equal. There is not a big change in it. Okay, so moving forward to the next point, that is transpose of multiplied matrix. Okay, so in the addition we see that the order of a matrix doesn't matter while we add the matrix, but in multiplication we saw that the order of how we multiply our matrix really matters. Okay, so the transpose of multiplied matrix is given by B transpose into A transpose. Okay, the order reverse is here. That's a point to be noted. Okay, so let's take an example of it. See, here I have taken two matrices A and B. Uh, okay, you can easily see here, and I have multiplied it, and you already know how to multiply it, so I'm going to skip it. So here is our resultant matrix AB, and if you transpose it, then rows are going to be converted into column, and column are going to be converted into rows. Okay, so in our theorem, we have a theory that it equals to B transpose into A transpose. So let's check it out. See, here we have the value of B transpose, that is 5, 6, and 7, 8 is second column, and A transpose is 1, 2 as first column, and 3, 4 as second column. Now we are going to multiply it and see whether it equals to the transposed value of AB multiplied. Okay, so here you can see that the both values are equal. So this theorem is also correct. Okay, so here is one thing to keep in mind, that while transposing a matrix which has multiplication operation in it, we have to reverse the order of multiplication. Okay, so moving ahead. Okay, so the next one is a square matrix. So number of rows must be equal to the number of columns to be called as a square matrix. Okay, and there are two types of square matrix. One is symmetric and the other one is skew symmetric. And if the transpose of a matrix equals to its original matrix, then it's going to be called a symmetric matrix. And if the transpose of a matrix equals to the negative original matrix, then it is going to be a skew symmetric matrix. But there is a condition for a skew symmetric matrix, that the diagonal elements must be 0 to form a skew symmetric matrix. You cannot form a skew symmetric matrix until you put the diagonal as 0. Okay, so moving ahead to the next part, that is inner and outer product. Okay, so there are certain rules for multiplication of matrices, that the number of column of first matrix must be equal to the number of rows of second matrix that we saw earlier. And what are the dimensions of multiplied matrix? Like if the first matrix is A A cross K, and the second matrix is K cross B. So here we can see, check that if we can multiply this matrix or not by rule number 1, that the number of column of first matrix, that is K, must be equal to the number of rows of second matrix, that is K. So K equals to K, so we can multiply it. Okay, so what will be the dimensions of the multiplied matrix? So there will be the first there will be the row of the first matrix cross the column of the second matrix. So here it will be A cross B. Okay, so moving forward to the multiplication. Okay, the inner product, or it is also called as a dot product or scalar product between two vectors, is obtained from a matrix product of a row vector times a column vector. A row vector can be obtained from column vector by its transpose operations. So here you can see that our u vector is a column vector and u transpose must be a row vector. Okay, so if we multiply it, then see, it is a 1 cross 3 matrix. It has 1 row and 3 columns, and the second one is a 3 cross 1 matrix, since it has 3 rows and 1 column. So our resultant matrix must be 1 cross 1. Okay, so the resultant matrix must have the dimensions of row of first matrix and column of second matrix. Okay, so it will be 1 cross 1. Okay, before going to that, there is one more term called a norm of a matrix or norm of a vector, that is defined by the square root of a transpose value multiplied by its original value. So here you can see that the transposed and multiplied value of u gives us the u1 square plus u2 square plus u3 square. So the norm will be the square root of this multiplied matrix, and I think it is pretty easy to understand. Okay, so if the norm of the vector equals to 1, then we can say that the vector is normalized. If the value of this addition is 1, then we can say the vector is normalized. And if the set of vectors are mutually orthogonal and normalized, we say that the vectors are orthonormal. Okay, so what is the orthogonal vector? Then if the product of, sorry, the inner product between two vector is 0, then we are going to say that the vector is orthogonal. And if the norm of a vector is 1, then we are going to say the vector is normalized. And if the set of vectors are mutually orthogonal and normalized, then we are going to say that the vectors are orthonormal. So these are the terms you should keep in mind sometimes. This will help you. Okay, then there is another product called an outer product of a matrix. It is given by U into V transpose. So here you can see that it has 3 rows and 1 column, and it is 1 row and 3 columns. So the output of the multiplication must be a 3 cross 3 matrix, and you can easily see it here. And it is the same operation like we did in our simple calculation in our matrix multiplication. Like we take the first row and first column and multiply it. So here it is u1 v1, then u1 v2, then u1 v3, then u2 v1, u2 v2, u2 v3, and so on. Okay, so moving forward to the part 6, that is inverse of a matrix. So this is a very interesting operation. It is easy to find inverse of a 2 cross 2 matrix. So here is a term called determinant of A, or determinant of a matrix, that is given by the multiplication of first diagonal or the primary diagonal minus the multiplication of the secondary diagonal. So the determinant gives us the value of our matrix. So here the determinant is going to be AD minus BC. So the inverse of matrix can be given by 1 upon determinant of A, and then we have to switch the positions of D and A, and then we just multiply the B and C value by a negative value. That's how we can get inverse of 2 cross 2 matrix. Okay, so that was an easy operation to understand for the 2 cross 2 matrix. But a 3 cross 3 matrix inverse is a little bit complicated process. But I have simplified it a bit so you can easily understand. So here is the 3 cross 3 matrix. So the M inverse, or the matrix inverse, equals to the 1 upon determinant of M into adjoint of M. Now adjoint is a new term for us, so we are going to see it with an example. See, the determinant is very easy to find for 3 cross 3 matrix. You just have to take the first element here, or the first row element here, and then we are going to skip this row and this column, means first row and first column. Then find the determinant like we find in a 2 cross 2 matrix. It is the multiplication of primary diagonal minus the multiplication of second diagonal. So this is going to be 0 minus 24. Then we are going to multiply our second element by by minus sign, only minus sign, not minus 2. So it will be minus 2, and we are going to skip the second row and second column here, and the left elements are 0, 4 and 5, 0. So we are going to find the determinant like we find in our 2 cross 2 matrix, and the same for the third element. So here how we are going to do it. So this is the third element. So we are going to skip the third, this the rows and column that includes the element which is 3. Okay, so this is easy to understand. Okay, just let me grab a pen quickly so we can understand it better. Okay, here we are. So okay, so for this matrix we can say that we are not going to include this row and this column. So the leftover elements are 0, 1 and 5, 6. So we can easily multiply it. 0, 6 is 0 and minus 5, 1 is minus 5. Okay, so for next one, suppose we are going to find a value of this element. So okay, so what we do here is skip this row and this column. So our main element was 1, so we are going to multiply it by 1 and find the determinant value of this element. Okay, so I think this is easy to understand now. Okay, so moving forward to the adjoint part. Now the adjoint operation is very easy to understand, but you just have to be focused on what you're doing. Okay, so first we are going to find the determinant, like we find in our 2 cross 2 matrix, or we just find here. Okay, so for the first element we are going to skip the first row and first column here, so it gives us the 1 6 and 4 0. And for second element we are going to skip the second row. Sorry, let me grab pen here so it will be easy for us to understand. Okay, so for the first element, or we are going to find the element which is going to be here in our adjoint. So we are going to skip this row and this column, so we left with this one, and you can easily calculate it. Now for this element we are going to skip this column and this row, so the left elements are 2 6 and 3 0, they are here. And for this element we are going to skip this row, sorry, we're going to see skip this row and this column, and the left elements are 2 1 and 3 4. Okay, so let's say if we want to find this element, what is the value of this element in our adjoint operation. So we are going to skip this row and this column, so the left elements are 1 0 and 2 1, you can find it here. Okay, so moving forward to the next part. Okay, let me just erase it. Okay, we are good to go. Okay, now we have the adjoint of a matrix defined by the determinant or the values we find here, and we have to multiply it by this sign matrix. So the sign matrix is pretty easy to understand. We just have to multiply the diagonals by positive sign and the non-diagonals value by negative sign. So here you can easily find the value of the the adjoint of matrix. And to find the inverse of the matrix here, we just have to divide it by the determinant of the matrix. So the determinant we find here was 1, so it is not going to make any difference in our adjoint. So this is our final operations that we performed in our inverse, how to calculate the inverse of a matrix. Okay, so the points to keep in mind here is to multiply it with our adjoint sign, and here we see how we calculated the value of each elements here. Okay, so moving forward to the part that is the Gaussian equation. Okay, so with Gaussian equation we can find the solution of this system of equation using matrices, and I have elaborated it pretty much. So we are going to see it line by line. See, first of all we have this three equations here. So in the next part I just take the coefficient of each of this, and then write it down as here. And this is this matrix -1 -7 and -6. And if you multiply, if you perform the multiplication operation, then you can see that this is this gives us the main equation back, right? First row into first column, that is -3x1 plus 2x2 minus x3 equals to -1. So we just wrote it in a matrix form. Okay, so now we are going to merge it, like we are going to skip this part, or we are going to ignore x1 x2 x3 and merge this y part into our main matrix. So I have written it down here. Okay, so now what we have to do is convert our matrix into a upper triangle form. Okay, so in our upper triangle form, the values, like, okay, let me go here. Okay, so this is our upper triangle form, so these values must be 0. Okay, so how we can perform it? So there is a technique called row reduction of a matrix. So here are the rules of row reduction. Okay, you can change, you can interchange the order of any row. Means you can put the third row here in the place of first row, and like you can interchange it, right? um, Put the first row in place of third and the third row in place of first. Okay, and you can multiply any row with a constant, and you can multiply any row like 2 4 of any number, like. And the third rule is that you can add multiple of one row to another row. Like you can multiply the first row by 2 and then add it to second row, or add it to third row, and so on. And these three operations do not change the solution of the original equations. So this is the thing to keep in mind. Okay, so the goal here is to convert the matrix A into upper triangular form, then use this form to quickly solve for the unknowns x. Okay, so here we are playing by the rules. So first we multiply first row with 2 and add it to the second row. So if you multiply this row by 2, then it is going to be minus 6, 4, minus 2 and minus 2. And we are going to add it with the second row. So our 6 minus 6 will be equal to 0, and same operations for the other. And then we are going to add the first row to the third row. So this is the first row and this is the third row, so this must be equals to 3. Let's check it here. Yes, it is 3. So if we add it here, then it is going to be equals to 0. Okay, so now we multiply the second row with minus 1 and add it to the third row. Okay, so if we multiply it by minus 1, then it is going to be 2, minus 5 and 9. Okay, then we are going to add it to the third row, then 2 minus 2 equals to 0, and the same operation for the other. Okay, so the original matrix has been converted into an upper triangular matrix. Now we can easily write the equation as follow. Okay, so now we know that the fourth column was the actual answer, or the actual y value of our matrix. So we can write it as here, like a minus 2x3 equals to 2. So we can easily get the value of x3, that is equals to be minus 3. So now we have value of x3, then we can easily get the value of x2, that is going to be 2. And now we have the value of x2 and x3, then we can easily get the value of x1, that is going to be 2. So we have found the solution for our system of equations to be 2, 1 and 1, where 2 is the value of x1 and 2 is the value of x2 and minus 1 is the value of x3. And if you put this values in our main equation, then you are going to then it is going to satisfy the equations, like 2 to n minus 1, then it is going to be minus 6 plus 4 and plus 2, then it is going to be equals to, no, we just did some mistake. Let me go check it here. Okay, so what is it? 2 to n minus 1. Okay, let me go here. Okay, let me grab a pen so we can easily understand. So the first is minus 3 into 2 into 2 equals to, sorry, let me just write it here. Minus 2 minus 3 into 2 is going to be equals to minus 6. The second one is also 2, so it is going to be 4. And the last one is minus 1, so it is going to be a plus 1. Okay, so 4 plus 5 minus 6 equals to minus 1. So we have got it here. Okay. So moving forward, I think this is quite easy to understand now. And if you have any questions regarding this operations, then you can put it in the comment section or you can mail me. I will put my mail in the description. Okay, so now part 8 is how to find the sum of square of each element in the matrix. Okay, if we multiply the matrix by itself, then it does not give the square of it. Okay, so to do to find the square of element, we have to perform a different operation, or we can say we have to multiply it with its transpose value to get the square of each matrix, sorry, square of each element. Okay, so now what we get here is the sum of square of each element in a matrix. So now why are we doing this, or why are we performing these operations? So let me put it this way. In our next video, we are going to see how the equation of normal, sorry, how the normal equation can be derived from the cost function that we try to minimize. Okay, so in that video we are going to use this function or this operation. So let's just get it here, understand it. Okay, so we have A and A transpose, that is pretty easy to understand. Now we perform multiplication between them, then we get 5 and 25 as diagonal values. So you can check it here that what is the value of 1 square plus 2 square, so that is going to be equals to 5. And what is the value of 3 square plus 4 square, so 3 square is 9 and 4 square is 16, so we get 25 here. Okay, so now what is the value of 11? So 11 is 1 into 3 plus 4 into 2, that is 8 plus 3 equals to 11. So both of these values are going to be same. Okay, so now moving forward to calculate the A transpose into A matrix. So it's pretty much the same operation, like 1 square plus 3 square equals to 10, and 2 square equals to 4 plus 4 square equals to 16. So it is going to be 20, and 1 into 2 equals to 2, and 4 into 3 equals to 12. So adding them gives us 14. Okay, so for vectors, we can easily find the sum of its element square easily. This is very useful operation in matrix, and we are going to use it in our next derivation. I mean in our next video. So let's find how it works. So here is our A matrix, sorry, A vector, and here is the A transpose vector. So if you want to find the square of its sum, then you can check it here. A transpose into A, that it gives us the value of 14. Then if you sum its square it element and sum it or add it, then it is going to be 1 square plus 2 square plus 3 square, so that is going to be a 14. So we get the same result here. Okay, so I think that this was pretty easy to understand. Okay, so here is the ninth and the last part that we are going to need in machine learning for now. Okay, so given that A and B are vectors, this is the point to be noted here, it must be vectors, then we can say that A transpose B equals to B transpose X. See, let's check it with an example. Here is A transpose B and B transpose, then we are going to multiply A transpose and B, then it is going to be 1 into 3 and 4 into 2, that is the value of 8. So we got it as 11. And the next one is a B transpose A, that gives us 3 4 into 1 2, so it's 3 into 1 plus 4 into 2 equals to 11. So both of these values are same, so we can easily say that the A transpose B equals to B transpose X. Okay, so I hope you guys enjoyed it, and in the next video we are going to derive the normal equation for linear regression using the concept we learned in this article. Okay, so in the next video probably we are going to find the slope and intercept of our system of equation, or what do we say, our data points, to find the best fit line using only matrices. If you watch my previous video, then you might have remembered that we did it by using Scratch Python, or we didn't use any Python libraries. And in the second video we used the scikit-learn library to perform operations that calculate slope and intercept values. So in the next video we are going to perform it by using matrices, and you will see it is very easy for us to understand it, and it is easy to calculate when we have our uh, less number of data points. Okay, so you can check this article here on my blog, and I will put it in the description to how you can view my blog here. And I have also some videos on my YouTube channel if you want to check it out, like simple linear regression and its derivation, and how to calculate the accuracy and simple linear regression using Sklearn. I think you might like this video very much, because I will also provided how we calculate the actual function, or how we calculate the slope and intercept without any scikit-learn library. Okay, and Okay, so that's it for this video, and thank you so much for watching. And if you want to view this article, then you can visit my blog, and I will put the link in the description. So thank you so much for watching, and I will see you guys in the next video.